Great. Okay. So in particular, okay. So let me start from the pilot challenge. At high Lumia LHC, we know that we will have about 200 interactions per bunch crossing with an average mu of 200. And this is how an event display looks like in terms of events. And as you may see, this is quite chaotic, and that's how, and that's why we started discussing about timing. As you may see here, it's very difficult to find the hard scatter events. So for this reason, high Lumia LHC is a really unique opportunity to test future frontier detectors such as 4D trackers. In particular, we know that timing detectors are a really growing area of interest in high energy physics, and here I'm showing a bunch of studies which are in plan for RAM 4 and on from ATLAS, CMS, LHCb, and so on. In particular, ATLAS will install ITK, which is without timing fully silicon tracker, plus AGTD, which is a timing detector in the forward region, and while CMS will install the MDT in RAM 4, and you can see later the talk by Ksenia. And so the next phase of, let's say, for the development is silicon trackers characterized by the 10 micrometers in resolution, spatial resolution, and 10 picosecond temporal resolution. So just a quick recap of how track is parameterized in ATLAS. And so right now, at the current stage, we don't have time as a part of the track parameterization, while it is added later on as a track decoration. We want to unfold this fourth dimension, which is an independent dimension, and this is what happened with the AGTD, which covers, as I said, the forward region, starting from the case without time, the left, and the center with the timing only, the AGTD. So what is AGTD? Is this high granularity timing detector, which will be installed in RAM 4, which covers between 2.4 and 4 in eta, and the idea is to remove mainly the pilot in the forward region, where you can see from this bottom right plot, the resolution with the ITK only in the terms of longitudinal impact parameter get worse. Okay, so let's go in the performance of HDD, and you see that it is based on the sensor, the LGAD, and it could guarantee from 30 to 50 picoseconds on the track time. And here you can see an example on DBF X2 invisible, where you see that the track time association rate is around 60%, and on the right plot you can see the resolution, the track time resolution as Rico minus truth. In terms of physics objects, AGTD is the first time that allows to have T0 of the vertex, and the resolution gets up to 22 picoseconds. So please remind this number for later, and on more than 50% of the track coming from hard scattered vertex. This also allows to improve the track to vertex association using the timing information, which can be extended as it's done as a kind of significance in terms of delta t divided by the sigma, the resolution on the track time. And of course, this has to be keep in mind that since the AGTD is in the forward region, this is not always possible to reconstruct the T0. In particular, you can see that on the X2 invisible sample, about 65% of the events will have a T0. Moreover, on other physical objects, it's the pilot jet rejection improvement. You can see here on the right plot that with the timing information, we can increase on jet tagging a pilot rejected by a 50% improvement with, for a given, for example, 85% of efficiency. And of course, I want to stress the point that this requires a precise measurement of the T0. So when saying so, because we actually don't have hermetic coverage in time, and while we have been studying this for studies, let's say, beyond RAM 4. So what if we have timing and hermetic coverage in ATLAS beyond AGTD? So this can be made eventually only after RAM 4, when the two innermost layers of ITK could be replaced, have to be replaced, and could be replaced with timing information eventually, and due to the harder radiation after about 2 inverse atom Barnard data at high luminosity LHC. And so this study is mainly regarding how precisely we can determine the vertex T0 on all the events, and if so the physics impact. So for example, if we can improve bit tagging as a study. So in terms of vertex time resolution, in this case, we associate the time to the tracks with a very simple truth association, and then we apply a smearing to emulate the track time smearing, and then we compute on the vertex, we compute the time of the vertex as the weighted average of the track time associated to the vertex. And then if you compare the case with all the tracks with the red case, which is the ideal case on which we are able to remove all the pileup tracks, we see that with a clustering very basic algorithm, which emulates essentially a 4D vertexing, while it is a 3D plus 1, we are able to reach about the ideal case. So we managed to go about to 7.2 picoseconds. And if you remember, the AGT case was about 22 picoseconds, which is, so it could be much be improved with this hermetic coverage. So in terms of flavor tagging, here I want to show a study, let's say, based on the state-of-the-art tagger in ATLAS, which is this GN2. Actually, this study has been made on GN1, which was the state-of-the-art tagger at that time. The idea is that we know that pileup is produced randomly along the Z, so we'll contaminate mostly the longitudinal impact parameters, and you may see that on the left plot, if you are able to remove by hand the pileup tracks from light and B, the discrimination will improve. And this is feed into the state-of-the-art network, adding this time variable to the track, which is the time significance essentially, which has this distribution. And from this, we can see what are the performance comparing the case without time, this GN1 ITK, and the GNT, which is the GN1 plus the time significance. And here you can see a bunch of results, which is how we usually give the results in terms of flavor tagging. And you may see that we are displaying the light jet rejection as a function of bit tagging efficiency, and for the different cases. So the black line is the case without timing, while the red, blue, and yellow lines are for different track time resolution cases, going from 30 picoseconds to 90 picoseconds. And you may see that still with lower resolution, so up to 90 picoseconds, we still have a significant improvement in terms of flavor tagging. In terms of understanding what's going on, we can study the jet pileup contamination, which is defined as the ratio between the number of pileup tracks in a jet divided by the total number of tracks. And as you may see from the grayish histogram, this distribution peaks at 0, which means that most of the jets are clean, but still we have a tail at high pileup fraction, meaning that the jets are contaminated. And as you may see, with the increasing of the jet pileup fraction, I'm showing on this plot the light jet mistagrate. The light jet mistagrates increases with the GN1 case, which is the case without time. While if we are able to include the timing information, you see that the light jet mistagrate improves as a function of the jet pileup fraction, which means that we can improve a lot with timing information. Okay, that was the animation. In terms of physics case, so we know that high luminosity LHC is a key point for the Dye-Higgs program, measuring the Higgs self-coupling. And here I want to show a plot, a very recent plot from ATLAS on the BB gamma gamma channel in terms of the performance, the significance as a function of bit tagging improvement. And as you may see that if we are able to improve about 4% in the tagging efficiency we could get on top of Gen2, which is the state-of-the-art tagger. We could improve about 5% more in terms of, for example, significance. Of course, as this study is for beyond RAM4, we need to take into account that this could eventually only be possible on partial Hilum LHC statistics. So, as I said, this is a physics case, but for the tracking has a lot of use cases. And this is a slide from last year, Valentina's talk. So, of course, we have a lot of interest in Hilum LHC, but there is a lot of interest also on other physics cases and also beyond LHC, in particular for future colliders. That's why I want to pass on a topic on independent-based algorithms and softwares, in particular ACTS, which is a common tracking software. And this is an open source library based on modern C++, which has very minimal external dependencies. In particular, it provides an open source open data detector, which is a generic silicon-based tracker. But it also so it has it's very fundamental for ATLAS because so first of all it supports ATLAS ITK simulation. You can see the reference. But currently in run 3 we are already using vertexing from this from ACTS, which is this MVF algorithm. And for Hilum LHC this is will be fundamental because the whole tracking will rely on ACTS for Hilum. So about the track parameterization in ACTS, comparing to what I showed before, here we have a complete, so ACTS provides a complete parameterization of peri-G, including time. And so this parameterization allows a very efficient calculation of the, let's say, the track's time arrival at the heat, at the sensor. And this time can be integrated in the measurement into the, for example, the Kalman filter tracking process. About the tracking performance here, I want to show that so the tracking performance with the open data detectors are fine. And on the left plot, you can see how the track resolution on single muons events and how it changes for different PT of the muons. And on the right plot, you can see that we are able to use the timing information for the finding and the fitting. And here you can see the pool. The red box is the pool for the time fitting. So how can we use time? So this can be studied on the open data detector to provide, as I said, independent study on this. And so heat time information can be used at different stages. In particular, here I want to show a usage in a study that we had on the seeding. And we know that seeding is very computationally expensive. And here you can see that using the track time on the LDD on a TT bar sample with pileup about 200, we can improve a lot the fake rate and the CPU timing from, you can see this from this two plots. You cannot see the mark. Okay. So in terms of finding, vertexing, let's say vertexing is split in two parts. One is the finding, the other is the fitting, and the vertexing is the way we are able to find the collision points and interaction points for the primary, but also it regards the finding of the secondary vertex, so the position of the decay of particles. In particular, the secondary vertexing is still missing in ACTS, but will be soon implemented. So there are two finding algorithms. One is the iterative vertex finder, and the second one is adaptive, so the one that is still is also used in ATLAS. And this, so with this algorithm, it is possible to use time in these algorithms to exploit let's say to exploit the separation in cases where the distance between the vertices is very close, so in very dense environment. So you can see here that in the case you don't have time, you could have multiple vertices very close to each other. The red dot points are the truth collisions, and in the case with time, if you extend this in the vertexing finding, you can include time, you can improve a lot because you have an extra degrees of freedom. In terms of fitting, also so time can be used and to improve the fitting, and ACTS has a complete 4D vertexing fit, and this is an analytical calculation of the Jacobian, and the performance, as you may see from the pool on the right, are very good, and also there is a maximum likelihood approach that can be taken into account to correct for different mass hypotheses of the track particles. In terms of results, here on the left, I want to show the two, let's say, two curves for the efficiency as a function of the delta between the two vertices on muon events. And in particular, you can see that with time, the efficiency increases a lot when the two vertices are very close to each other. And this means that time can help a lot in very dense environment. While on the right plot, you see that there are two seeding examples, so two different grid seedings. And in the case on the, let's say, left plot without time and the right plot with time, and you see that with time we can have a higher reconstruction efficiency with a lower CPU budget. And of course, there are a lot of studies ongoing. Some I put in the cap for let's say timing, and so I will go to my conclusions. And this presentation shows, let's say, the impact of track reconstruction with timing on a physics program at High-Lumi LHC, and we know that modern detection algorithms are really solid against PILAP, as I shown with the ITK, but of course a fraction of PILAP is still observed. That's why this let's say pushed us to go towards this 4D tracking, which with an hermetic coverage, but also let's say HETV studies, and they can potentially improve a lot the performances, impacting the physics case both for the High-Lumi program, but as shown for the with ICTS also for Future Collider. And of course, this is also a very hard technology challenge that requires also a great effort in research and development. And that's it from my side. Thanks.
Okay, thanks, Lorenzo, for the very interesting talk. Do we have any questions for Lorenzo?
Yeah, basically I have a question. So yeah, I have a problem in understanding of all these performance improvements. So what we have shown is that timing resolution is approximately 7 or 8 picoseconds. Sigma in the best cases, but 1 picosecond corresponds to 300 microns. Then if you translate this into the, let's say, primary vertex resolution, you get something like 2-point-something millimeters in longitudinal direction resolution due to the timing. Then what we have shown on the page 6, approximately, tracking resolution in this region, longitudinal tracking resolution is of the order of less than millimeter up to eta equal 3 or even more than 3, and it's definitely better than 2 millimeters. So basically, tracking resolution by itself is much better than the resolution provided by timing. And moreover, this timing resolution is of the order of 2-point-something millimeters. So if you provide a vertex density, so 1.6 millimeters, so I guess it's for the round 4, where PILAP is 200, so I guess vertex density should be much bigger. And then vertex density is significantly much bigger than the resolution provided by timing. And then, so honestly, I have a sort of problems to understand how this timing resolution of that order can improve the tracking resolution, which is by definition much better than the, let's say, this space resolution provided by timing. It's, it's basically sort of conveying this reasoning, but so indeed, I don't understand. So I understand formally that you just inject your timing resolution and your track reconstruction and vertex reconstruction, etc., and you get this improvement. But let's say from physics point of view, where this improvements comes from, taking in mind, let's say, taking into consideration all these, let's say, scales of resolutions provided by timing and tracking.
I think you probably have the plot of the density somewhere in the back.
And just maybe that's the.
No, but in any case, with resolution already, so tracking resolution is this. I naively assert that tracking resolution is worse than the resolution provided by timing, but in fact it's not. It's better.
That it is better at this stage. I think the point here, Vadim, is when we look for the decay of the beats, they will be displaced. So regardless of the track resolution, the place where you see them entering is on the tails of the.
No, but we're discussing primary vertex resolution.
On the primary vertexing, the point remains that you have them overlapping in space. So
yeah, but let's say this overlap means that the distance between the vertices is less than the 100 microns.
And
then I don't understand how this overlapped vertices can be resolved, keeping in mind that timing resolution is more than 2 millimeters.
The point is that you are not resolving them in space, while in time, since the beam spot is around 180 picoseconds, if your track vertex resolution goes even up to 22 picoseconds, whatever, the worst case, if you're able to have this information, you can have the same point in Z, but still you have in very different time. So you manage, for example, to cluster them in 2 different time space points.
Maybe just show the plots of the Z.
Yes. I don't know if this is the question. So
this is probably going the direction you're trying to bring the discussion on. So if I understand correctly, your question is that given the Z resolution you have, you should be able in principle to distinguish vertices given a certain palette density, even without the usage of time. This is the comment you made? Yes. Okay. So I think that the problem might be in how you try to find the collection of tracks you want to use for fitting a vertex. So during vertex finding, what might happen is that you will try to cluster together tracks. And it might happen that that cluster that you use for seeding to produce a vertex, you merge together 2 blocks of tracks. So there are many ways you can do that. There's the grids approaches, local density approaches, or whatever you want to do. But it's been seen that with let's say the default values that you pass. So I'm not saying that there is no optimization that can be done and no investigation to see if with only space and better tuning of the seeder, this can be resolved. But with the default things that you have, you can see that you might lose vertices because you tend to lose capabilities to find disjoint local maxima that you can use for your vertex. That's what is more or less you go to see here. What you see here is that without time, you start to lose vertices at about 200 millimeters. Now, as you know, the vertex Z resolution, once you feed it with multiple tracks, has a better resolution than 200 millimeters, the 200 microns. The fact is that it seems like you're losing them during the seeding stage, which is more or less the window that you allow for having these joint blobs. When you have time, then you basically have another direction. So you can kind of make these blobs in a 2D grid. And that's why you recover some of those vertices in that case. So this doesn't mean that given the single Z resolution, you cannot come up with a better and smarter seeder to increase your vertexing. What I'm saying is that with the current studies, with the current seeders, with a certain type of configuration, this is being found. It's not been investigated to the last bit, but the indication is that vertices are likely to be lost during this seeding stage. Does it maybe goes in the direction you were trying to investigate? Trying to probe, let's say, maybe?
Okay, basically, I understand this idea. So you would like to decrease multiplicity of tracks due to the timing. So you just select maybe, let's say, tracks which are close in time, but those are forward tracks. And resolution in the primary vertex reconstruction is defined by tracks at, let's say, EP equals 0, which have much better the resolution And basically, you can have, let's say, a collection of overlapped tracks with distance between those tracks of the order of 100 microns or 200 microns. So in best case, so it's okay. So what you have, let's say, in 1 millimeter, you have 10 reconstructed primary vertices in ideal case. And then you need to assign to those vertices tracks this time. How you do this? If your timing resolution is of the order of millimeters.
But okay, so
So
can I
that's
interject?
so I'm not claiming that it's impossible. I miss a sort of hand-waving naive understanding how it works.
Maybe I can clarify this, Vadim. I think the issue here is that you're thinking of time as a measurement of space, which is not the case. You know,
right.
You're obviously right that the zero resolution is much better than time resolution, but we are not using time as a handle for the Z position. Time here is totally orthogonal. You have to think about this as a two-dimensional problem. So you have a 50 millimeter beam spot in Z and a 180 picosecond beam spot in time. So the feature of time that you are using is that the different vertices occur at different times on a scale of 180 picoseconds. So it's a completely orthogonal. You should not think about timing and Z as a correlated variables. They are uncorrelated, and this is why timing is powerful. So 30 picoseconds divided by 180 picoseconds is a factor of 6. So basically, you're reducing by a factor of 6 the amount of pi. And so what I'm trying to say is that your comment is correct, but here I mean you have to keep in mind that this is a 2D problem.
So can I interject and just say, in the interest of time, I would suggest that we maybe have more of this discussion after the seminar, because we want to leave time for potentially other questions and also our second speaker. But thanks for the clarification and the discussion. Okay, are there any other questions for Lorenzo? Maybe I had one quick question that you may or may not know the answer to. Do you know if, are you personally working on the secondary vertex algorithm in ACTS, or do you know if someone is actively working on that right now?
I am not, but
Okay.
here there are
Unfortunately, no. Unfortunately, the vertexing, the actual algorithm development is really short on person power, and we don't have anyone working directly on secondary vertex.
Okay.
Very short person powers.
Okay, are there any other questions? Not, I would say let's thank Lorenzo
Thank you.
for the very nice talk and move to our second speaker.
Stop my sharing, which I don't see my cursor. I don't know how. Okay, thanks.
Okay, thanks. So our second speaker will be Ksenia, and she will talk about 4D tracking at CMS.
Yes, hello everyone. I hope you can hear me well.
Yes, we can. So please take it away.
Thanks. So yeah, today I will give you a presentation on how the tracking and vertexing at CMS. So that's the outline of this presentation. So I'll start with a brief introduction on the motivation, so high Lumi LHC, and the new MIP timing detector that will be introduced in CMS, and then move on with the discussion about the tracking with timing and the 4D vertex reconstruction. And finally, I will show you our recent developments in the 4D algorithm and some performance studies. So yeah, let's start with the motivation. As we already heard in the previous presentation, at the high Lumi LHC, we will have a very high instantaneous luminosity, which will translate in a very high number of pileup interactions, between 140 and 200 expected. And it will be important for us to isolate the interaction of interest among all of them and to mitigate the effects of the pileup on all the object reconstruction that are useful for performing physics analysis. And the way to do it in CMS is to perform a very precise track vertex association. Just to give you an idea of what we're talking about, I'm showing on the figure on the left-hand side the pileup profile that we have in run 3 and we had in run 2. And currently in 2024, the mean number of interaction is around 60, while we will have much higher numbers in HiLumi. And this is a picture of a high pileup run event recorded by CMS, showing the how events will look like. So to introduce a bit the idea of the use of timing for the tracking and vertexing. So the idea here is to use the timing information to separate the vertices that overlap in space. And this will be possible because our modern detector technologies allow to have around 30 picosecond time resolution. And this is actually smaller than the spread of the proton-proton collisions, which in space is around 5 centimeters. And it translates in time in a spread of around 170, 180 to 200 picoseconds. So that's why the separation is possible. And this can be visualized also in this figure on the right-hand side, where we have on the x-axis the z coordinate, and on the y-axis the time coordinate. You see all the vertices here, the simulated vertices as red dots, and the vertical lines represent the 3D vertices. So you can see that we will have a lot of vertices that are actually overlapping in space. And that's where the timing information will be useful, because with the addition of the time coordinate, we will be able to separate the overlapping vertices. This means that if we move from the 3D vertex reconstruction to the 4D vertex reconstruction, the effective pileup contamination that we will have will be reduced. And this can be also seen on the figure on the left-hand side, where you have the number of pileup tracks per primary vertex. And you see that without the use of timing, so the blue dots, would have a very higher number of tracks, while with the inclusion of timing, we will go down and reach a level that is comparable to the one that we have now in run 3, let's say. So we will have same pileup environment, for which we already developed very nice tools that they work very well for pileup mitigation. So the detector that will provide the timing information is MTD, so MIP timing detector, which will be used to measure the time of charged particles. It will be placed between the tracker, the inner tracker, and the calorimeters, and it will have an almost hermetic coverage with eta values up to 3. So the central part of the detector, the barrel timing layer, or BTL, will be made of isobars with 2 SIPMs per bar, with eta going up to 1.45 and measuring time of particles above 0.7 GeV in transverse momenta, and an active area of around 38 square meters. While on the two sides, we will have the end cap timing layer, or ETL, which will be made of LGATs with eta that goes up from 1.6 to 3, and an active area of 14 square meters. So with MTD, we are going to be able to measure the track time. And here I'm going to explain how the track reconstruction with timing is performed. The first step is the local reconstruction. So in BTL, this translates in single crystal measurements, and the time will be then computed as an average of the left and right SIPMs measurements. While in ETL, we will have pixel measurements. So after the local reconstruction, we are going to perform the topological clustering of adjacent MTD hits. In BTL, it will be possible to have multiple hits, especially at higher eta, as can be seen on the figures here on the left, on the right of the slide. while in ETL, we will mostly have single hit clusters. And the cluster time and other properties are computed as averages of the single hit measurements. So the cluster time is the average of the weighted average of the single hit times. So after reconstructing our clusters in MTD, we have to perform a matching between the tracks that we reconstruct with the tracker and the MTD. So this matching is performed both spatially, where a spatial matching is made based on the chi-square of the track extrapolation to the MTD surface, and also checking the time compatibility with the beam spot constraint, which is used to suppress background mainly, and will be optimized in the future also for searches, so for heavier decaying particles. The matching of the tracker tracks to the MTD clusters are assessed with a BDT to assess the quality. And we can select tracks with high matching quality with the MTD clusters. So once we have our tracks made of tracker tracks and MTD, we are going to refit the track parameters, including this additional space measurement of the MTD surface. And afterwards, we can compute the path length. For each track, we are going to have the path length and, of course, the momentum, but the velocity depends on the mass hypothesis, which a priori is unknown. So what we do is to propagate the time from the MTD surface to the beamline using various mass hypotheses. So we choose pions, kaons, and protons being the most probable ones. And this actual propagation is dedicated to our primary vertex reconstruction, while a similar approach may be used also for secondaries exploiting their known position. So each track is going to have a time assigned, but with the time we also have the track time uncertainty. So the total time uncertainty for each track is given by different components. We have the MTD time uncertainty, we have the time of flight uncertainty, and we have an inflated uncertainty, of which I will going to talk in the next slide. So the time of flight uncertainty in particular is just the propagation on the uncertainty on the particle velocity that derives from the reconstructed track momentum. And this is also dependent on the particle hypothesis. However, different studies have shown that the overall time of flight uncertainties on the track time has a negligible impact on the reconstruction. So with our tracks with timing, we can finally perform the 4D vertex reconstruction. And let me remind you that the 4D reconstruction and the particle identification go hand in hand, because given the track time, we still, at the MTD, we still don't know its mass hypothesis, so the actual time at the beamline is unknown. What we do to overcome this ambiguity is to use the constraint that all the tracks that come from the same vertex should have the same time. So until recently, the 4D vertex reconstruction was performed in 2 steps. So what I call here the legacy 4D. So in the first step, we were using the pion hypothesis for all the tracks to cluster the vertices in 4 dimensions. And here we have this inflated uncertainty that comes from this assumption that we made. And this uncertainty is just the difference in the time of flight between the proton and the pion hypothesis. So with this first clustering of the vertex, we can calculate the vertex time and perform the particle identification, which means that we can check the compatibility of the track to the various vertices in the different mass hypotheses to check which is the most probable hypothesis. And afterwards, we go to the second step where we cluster the vertices again, this time using the updated track times and removing this inflated uncertainty. And again, we can calculate the vertex time and check again the particle identification. However, this algorithm is not the optimal one, because it is CPU time consuming, because in this first step that we perform, the MTD uncertainty is smaller than this inflated uncertainty that we had given by the assumption of the pion hypothesis. So for low momentum particles, this inflated uncertainty dominates and basically makes the use of timing of limited use. Moreover, some studies showed that this legacy 4D vertex reconstruction performed worse than the standard 3D vertexing. So we recently updated our algorithm by removing the first step of the legacy 4D with the 3D vertices. And this is possible because we have now a time computation that is available also for the 3D vertices that I will explain in the following slide. And this is useful because we just need one initial vertex time to be able to obtain the correct track time for each track. In this way, it's also possible to reduce the CPU time of around 30% because we remove one of the three vertex clusterings that we have, because we still have the 3D vertices and we had these two steps of 4D. So in this way, we are more efficient. And the overall algorithm that we use for the actual time computation is also updated, which shows an improved vertex time resolution. So how is the time computed for vertices? So in the previous version, in the legacy 4D, the vertex time was computed just as a weighted average of the track times using the best hypothesis for each track. While now we have deterministic annealing type of time algorithm, where we use all the three mass hypotheses at the same time, and we minimize this cost function, where we have different terms that enter. So we have first the track weight that comes from the adaptive vertex fit. And then we have three terms, one for each particle type, where for each track we have the time in each hypothesis, the uncertainty in each hypothesis, and we set some a priori probabilities for the track for the particle type, which come from the expected abundance of each particle type. And this kind of algorithm is applied on top of the already reconstructed vertices. So we can use it on top of 3D vertices that were clustered only in 3 dimensions, but also for the 4D vertices that are clustered, also including the time coordinate. And with this new time computation, now I'm going to show you some performance studies that we performed. We used a simulated TT bar sample with 200 pileup. And we are showing here the results for our updated 4D algorithm in orange, the 3D with the time calculated afterwards in blue, and the previous one, the legacy 4D in red. So here we start with showing the signal vertex time. So on the left-hand side, we have the vertex time resolution, and on the right-hand side, the pool. For signal vertices, we performed a fit with a double Gaussian function, and here we show the results of the narrowest one. And in general, we see that the updated 4D and the 3DT show an improvement both in the resolution and in the pool with respect to the previous algorithm. And we also reduce the negative bias that was there in the legacy 4D, which was due to the misassignment to the kaon or proton hypothesis. And this bias is reduced now because the new time computation allows the accounting of all the mass hypotheses at the same time. We checked the number of reconstructed vertices as a function of the number of pileup vertices. And we show it here for real vertices and fake vertices. And the real or fake categorization is based on the matching that we perform to the MC truth. And this matching is based both on the true particles and on the true vertices. Here in general, we see that the 3D algorithm reconstructs more real vertices, but also more fake vertices, while the updated 4D has a performance in between the 3D and the legacy 4D. So we can reconstruct more real vertices compared to the previous algorithm, but also some more fakes. However, what is really interesting to see is the distance in Z between pairs of reconstructed vertices. And here again, I show you the results for pairs of real vertices on the left and pairs of fake vertices on the right. And yeah, the 3D algorithm itself is not able to reconstruct vertices that are close to each other because by construction, it cannot separate vertices with separation below 0.3 millimeters. While with the 4D vertexing, it's really possible to reconstruct vertices with delta Z close to 0. So these are vertices that are spatially overlapping, but thanks to the use of timing, they can be separated. And here we actually can see the improvement in the use of timing. Finally, we also checked how this algorithm perform in terms of the pileup rejection, which is really important for high luminal HC and one of the primary goals of MTD. And we checked it for track-based observables and jet-based observables. So first, for the tracks, we classify them again based on a matching to the MC truth as tracks coming from a primary vertex, from a secondary vertex, tracks, pileup tracks, or fake tracks, meaning that they are not matched to any true particle. While for the jets, we build, let's say, with a simplified procedure, we build our track jets by clustering together all the tracks that originate from the same vertex. And we can compute the relative contribution of pileup to these observables by reclustering the jets without the pileup tracks and computing the observables again. So here I'm showing you the results for, again, for the leading vertex. And I show you the relative contribution of pileup on the track multiplicity on the left-hand side, on the jet multiplicity in the center, and on the sum of PT square of jets on the right. And for the first two observables, we see a reduction in the pileup contamination in the 4D algorithms with respect to the 3D. So here we actually have less pileup contamination as expected, while we have other variables that are less sensitive to the choice of the vertex reconstruction algorithm. Like, for example, this one, which is the sum of the square of jets, which is important because this is the variable used for the vertex sorting in CMS. Okay, so with this, I come to the conclusions. I showed you how the use of the timing information from MTD will be important to mitigate the effects of pileup in high luminal HC. We have our set of tools that we developed to evaluate the performance of different vertex reconstructions algorithm. So to check the vertex time resolution, the number of reconstructed vertices, and how the pileup rejection behaves in different vertex reconstructions algorithms. And these are important for us to set a benchmark for future developments and also the use of new techniques in the vertex reconstruction. And with this, I hope I convinced you that the use of timing will be important for the vertex reconstruction, as the vertices that overlap in space will be separated with the use of timing, and so also improving the pileup rejection. Okay, that's all from me.
Thank you for this interesting discussion. Does anybody have any questions? I see a hand in the room.
Yeah, so thanks a lot. This is the third time I see this talk, and I think that finally I'm getting a grasp of what you guys are really doing, and I think it's awesome. So going back to the part where you show the max likelihood. So I've tried that, and So I've tried it myself, and I found a couple of things. So first of all, the question I have is how really is necessary to use deterministic annealing iterations here. I've tried it with and without just performs more or less the same. So I know that CMS uses a deterministic annealing approach to vertexing, but I really wonder if it's really needed in this case. I mean, I know why you have it, but I was wondering, did you try it with and without? Because if you see the same performance, then you can still save more CPU time instead of doing multiple fits.
Yeah, so we actually tried to just change the time algorithm. So with, let's say, with the usual 2 steps of the vertex reconstruction. So on top of the reconstructed vertices, we try to use the different time computation algorithms, and we see an improvement. In particular, we see an improvement in the bias. So using
this I understand. The deterministic annealing part of that likelihood, if you go back, is the T, is the temperature, right? If you remove the temperature and you just do a single fit, do you have the same? I've tried it and I saw that very similar results, and I was wondering if you tried it as well, or you really need to put a temperature and iterate over the temperature to get a proper result.
I see. I get your question now. No, we didn't try that. So we didn't try to remove the temperature and the minimization. But that's something that we can for sure check.
Okay. The second question I have is related on how many tracks do you need to have a stable fit per vertex? Because I've seen that since you're adding several parameters, then you need to have at least, I don't know, a few tracks per vertex. Since you have many, so for our case in Atlas, I don't know if it's going to be good to apply this because we don't have many tracks per vertex due to the forward region. So do you know more or less if you have instabilities in this fit due to a low number of tracks per vertex? Do you have like pathologic cases?
So this I wouldn't understand, but I'm not sure if I got your question right. So let me just iterate again that. So this part here is only to the time computation. So we still compute the vertice, cluster the vertices in 4D beforehand. And after we cluster the vertices in 4D, we use this only to compute the time afterwards. So this is not part of the...
Yeah, I understand that. It's just that this fit, I've seen in my test that you need to have at least 5 to 10 tracks per event, per vertex, in order to have a stable minimization. And my question was, do you have pathologic cases where you have, let's say, just a handful of tracks per vertex where the fit doesn't converge?
Yeah, this I wouldn't know.
Okay.
We can check that.
Okay, sorry if I can comment on this point. Fabio Cossuti from Trieste speaking. Most of the vertices, of course, let's say we have probably a wider coverage, so we have also the information of the central region. Let's say clearly there is a minimum selection on the numbers of degrees of freedom you have seen in the vertices that are selected, so we are cutting those of very low multiplicity. And clearly, this helps in getting a minimum number of tracks with time. This algorithm that you see, of course, one can explore it. One can explore many different possible ways of computing the time of the vertex. You say that you've tried a simple likelihood. It's working similarly well. This, if you want, is essentially the part of a deterministic or a global deterministic annealing that you could have that was studied to do a complete one-shot clustering both in space and in time, taking into account all the hypotheses.
Okay.
Yeah, the real problem there is that it turns out to be computational, at least when this was explored, it turned out to be computationally very heavy and problematic. This is the reason why we reverted to this two-step approach for the time being. So let's say this temporal part is explored in this way, and this part actually is very quick. So it's not here that we are wasting time. Mm-hmm. This is quite quick because it's performed a posteriori on the vertex, and you can perform it on any vertex. Obviously, if you do on the 3D vertex, there's no benefit in the paid-up rejection, right? So you are computing the best time of that object, whatever that object is. The other part, on the contrary, we are using just one time hypothesis. Of course, this introduces the problem of deciding which time hypothesis. This is the reason of the iterative procedure. This is not the end of the story. We are exploring possible future developments, but this is the state of the art that we have and that we wanted to present here.
Okay, and the really last comment, sorry for this as well, but have you tried to see if you have cases where you don't fix the initial probabilities, but you let them be extracted from the fit itself, and if that has been successful, given if you haven't tried that?
Okay, if I can go, let's say we were considering the possibility, for instance, to parameterize the probability. Here, this is a simple case where we fix them. We have considered the possibility to make a bit more sophisticated parameterization depending on the kinematics. This is not finalized, but to be honest, I doubt that this is going to give a large impact. Let's say what we studied, and Ksenia can comment on this because she explicitly did, is the choice of the relative probabilities, in the sense that you could also think to have a flat prior for all of them. Extracting them also from the fit, no. At that point, yes, I think that you would be much more dependent on the amount of time information you are in the vertex. In any case, Ksenia, you studied the flat prior, and that was not behaving well.
Yeah, exactly. Okay. Yeah.
Because you were at that point you were introducing biases.
Okay.
So it's something that you need to be a bit careful.
Okay, thanks a lot.
Okay, are there any other questions? We're just after the hour mark now, so maybe we have time for one more.
Can I ask a small one? Thanks again, Ksenia. I second what PF said. It's always a pleasure to re-listen to this and relearn. So thanks for the presentation again. I had a small question on slide 10, mostly out of curiosity. You show the fraction and the reconstruction time, and I'm a bit surprised that the reconstruction time for vertices is so big.
Yeah, maybe it's not entirely clear. So the total RICO of the total CPU RICO is 35%, and of these 10% is Reco vertex. So it's 10% of the 35%.
Okay, so it's a much smaller fraction. Okay, and this is the total RICO time, not only track reconstruction. This is for all objects you have on the right.
Yeah.
Okay.
Yeah, right.
Okay, got it. Thanks.
I had a very general question on magnetic detectors, and if you could, would you instrument every layer of a tracker detector with timing, or do you get diminishing physics gains?
Yeah, I think probably the most sensitive one for the physics case is it's also the beamline for example, for B-tagging, where you have you're close to the vertices.
Okay, so if you chose any layers, it would be the innermost.
Yeah, this is generally, for example, for B-tagging, but I'm not sure. Of course, if you have, let's say, if you have more layers, you can have a higher vertex precision versus time precision, because you have more hits, for example, in the central region than in the forward region.
But yeah.
Okay, yeah, so it also depends on the application.
I think Marco raised a hand maybe to respond to that also.
No, actually, I had another question, but I don't know if I can. It's for Lorenzo. At some point in your slide, you show the integration of time in ACTS as the sixth parameter in the Kalman filter, and I was wondering what kind of detector this development is targeting, and also if time is really part of the state that you use internally of the Kalman filter, and how do you propagate it?
Maybe I can forward this.
So in terms of the detector, I mean, we're not currently targeting any specific actual physical detector. So the development and the validation and so on is mostly done on this open data detector, where we use effectively hit smearing for digitization, and we can pick and choose exactly what type of time information goes. And then in terms of the treatment in the filter and also in the propagation, yes, it's part of the state vector, the numerical integration for each Roman-Cotta step also integrates the time basically between points and point. And then the Kalman filter formalism incorporates the predicted time into the state update, which is also really nice because we can treat the measurements. For instance, we can easily have unified XY time measurements that then affect the three dimensions of the track state in the Kalman filter. And we even this entire development is also carried into the global chi-square development, global chi-square filter development that's also ongoing.
But do you assume that the state on each detector will provide also time or not?
We don't assume this, no. We have a 6-dimensional local track parameterization on each surface, and then the detector and or experiment can decide per detector technology which dimensions are being measured. And then the Kalman filter and all the other filters will basically pick out the actual measured information from the sensor and then incorporate this. So there's no assumptions. Effectively, if you don't have timing information in your entire detector, it just is a spatial fit.
Yeah, basically every experiment can decide the projector on every surface.
Very last question on this topic: which mass hypothesis do you propagate?
By default, it's pions, but you can choose.
But then if you pick up, sorry, if you pick a pion and it was not a pion and it was low PT, you end up with
that bias. We have actually
with propagating a state which is wrong until you reach the timing measurements, basically. Yeah. And then what do you do?
Correct, yes. So this is, it's a bit of a cheating answer. This is out of scope of the algorithm. So right now the filter basically just runs with the particle hypothesis that you give it. And then there's a current, we're thinking about some developments to try and distinguish, say, good particle hypotheses from bad ones. But this is currently up to the caller of the fit to then deal with.
Are you considering GSF with all the mass hypotheses in one go?
We don't do this at the moment, but we've been talking
We were talking about that, yeah.
Okay, thanks.
Okay, let's go to one last question from Fabio, and then we
Yeah,
will
no,
wrap up.
so just linking to this question of Marco and the relative answer, I think that this development that you did is very nice, but is effectively interesting in the moment in which you start really having different time measurements at different layers. So I assume that your formalist is foreseeing the possibility to embed them with their own uncertainty. At that point, the obvious interesting development is to try to get rid as much as your time resolution allows from the need of a pi or mass hypothesis, because you infer directly from the track fit, right? So the time distribution along your path length is sensitive up to some resolution to the fact that your particle is a pion or a proton, etc. So that I think, to my humble opinion, is the interesting development of that part in view of your detector, let's say.
Yeah, mathematically it's possible. Within the CTS, that would require some restructuring of the algorithm. So the implementation might arrive, but
otherwise, the interesting part, okay, is that you can know the time at any place along the trajectory. That is also useful because essentially it allows you it's a general tool for a fast propagation of the time, but the main
I think
is
I think we had this conversation very briefly last Friday, and we discussed that we have in mind to look into this, but the idea would be to basically do a goodness of fit within 3 mass hypotheses when you have multiple measurements in your detector, more than actually derive directly the mass from the fit, since you also have just 3 masses, basically.
Yeah, okay.
This would be
the optimal way to exploit it. I have not clearly in mind that there are different possibilities that we can explore. But okay, that I think that in the future perspective, if you want to speak, because we are speaking on 4D tracking, we are not doing 4D tracking. We are just using time in some way to do the real 4D tracking. To me, is where you have multiple time measurement and you combine them in a clever way. And at that point,
I mean,
possibilities.
You are kicking down an open door. I always like this mathematical, the optimal mathematical implementations, but I also think that we can proceed a bit with steps sometimes. But I agree, it would be nice. Yes.
Thank you.
Okay. All right. Thanks everyone for the discussion. I think this was a very interesting seminar, and thanks again to the speakers for preparing the slides and starting the discussion. And I think we can wrap up for today, and hopefully we'll see everyone at the next HSF seminar in about 1 month. Thanks, everyone.
Thanks.
Thank you.
Joe.
Bye.
And bye-bye.